So our next example comes where we're looking at how do you find relative maximums and minimums. Extrema we sometimes call them. And if you recall from the graphs, that means we're looking to see where is the derivative equal to 0 or where is it undefined. So the first step here would be to take our derivative. Please note that in this example here, our derivative is going to require the quotient rule. With the quotient rule, we have the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So, with a little bit of cleaning up here, we get a derivative that is 1 minus the log of x over x squared. The next step here, of course, is to find those points where the derivative is 0 or undefined. I'm going to look at my critical values here and see what makes it undefined first. What could make that denominator equal to 0? And that seems to be kind of an easy part. The secondary thing here to think about is what would make my derivative equal 0? I don't mean the denominator equaling 0, I mean the whole thing. And if you want a fraction to equal 0, you just set the numerator equal to 0. If I roll this logarithm, x is going to wind up equaling e to the first power. So I have my set of critical values. In this case, there happens to be two of them, 0 and e. Now, once we get those critical values, we need to make a sign chart, figure out where this graph is increasing and decreasing. So very important here, we make our sign chart, we're going to plug some numbers in. This number might be easiest to use 1 because the only value for a logarithm I would expect you to know without a calculator is what's the log of 1? The log of 1 is always 0. So if I use 1 as an example here, I get 1 over 1 squared, that's positive. Anything bigger than e is going to give me a negative value. And lo and behold, take a look at the domain of this function. Logarithms must be positive. So if that's true, I know that there are no numbers below 0 that would even plug in. This gives me enough information to figure out it is increasing here up to e and decreasing after. Therefore, we have a maximum at e. Now, we also need to find the y-coordinate. To find the y-coordinate, we probably need to plug that x value, e, into the original, the one that actually says y equals. When we plug it in there, our answer for the y-coordinate is 1 over e. There we go. Also, I want to remind you about inflection points. So to get the inflection points needed, we probably need to find the second derivative. Once again, take your critical values. Pause for a moment if you want to try this one. Take the second derivative and find those critical numbers. So here's my second derivative. Once I found, using the quotient rule again, I divided out one value, one x from each term, top and bottom. That's going to simplify this a little bit. Then, when I do some algebra here, I get some nice numbers and I just reorganized it. To get those critical values, look to see what makes the second derivative equal 0 or where it's undefined. Undefined is easy. That's what makes the denominator 0. However, finding out what makes the numerator 0, thereby making the entire function 0, oh my goodness, if I were to roll that logarithm, whoops, I would find out that my last critical value is e to the 3/2. What a nice, easy number to work with. So we put together this nice little sign chart. Notice I am not including any numbers smaller than 0. We already talked about the domain. Domain can only be positive real numbers. So looking at that, we have something that's concave down. It changes to concave up. We have an inflection point at e to the 3/2. And to get that y-coordinate, once again, plug it back into that y equation. And you get a y-coordinate of 3 divided by 2 e to the 3/2. Yay, we've reviewed how to find men's maxes, inflection points, all that good stuff. Gosh, that was half of chapter 3. We just did that in less than 5 minutes. Congratulations.